Hi guys, in this presentation we are going to learn about quantum computing for finance, state of art technologies and its future prospects. So before that, let me introduce myself. I am Sai Krishna. I am currently a student who is pursuing data science bachelor's degree at IARE. So what are the objectives of today's presentation? Well, we will first introduce ourselves to quantum computing and its inner working. Then we will understand what are the fundamental steps for quantum computing. Then we will have a brief introduction over finance sector. Then only we will be able to pursue its needs and understand the applications where quantum computing is necessary and its future benefits. So let's start with introduction. In the financial services industries, there are many computationally challenging problems arising in applications across asset management, investment banking, and retail and corporate banking. Quantum computing holds the promise of revolutionizing how we solve such computationally challenging problems. All computing systems rely on a fundamentally ability to store and manipulate information. Absolutely. So, inner working, how actually these quantum computers work. Today's classical computers manipulate individual bits, which store information as binary 0 and 1 states. Millions of bits work together to process and display information with a speed that everyone is familiar with on smartphones, laptops, and servers in the cloud. Quantum computers use the physical phenomena of nature to manipulate information via quantum mechanics. Today's classical computers manipulate individual bits, which store information as binary 0 and 1 state. Millions of bits work together to process and display information with a speed that everyone is familiar with smartphones, laptops, and servers in the cloud. Quantum computers use the physical phenomena of nature to manipulate information via quantum mechanics. Multiple qubits may be purposefully entangled into linear combinations of complex valued weighted states across the qubits, which correlates them so their quantum state cannot be described independently, that is, entangled states. And quantum interference allows to bias the measurement of a qubit towards a desired state, thus controlling the probability a system of qubits collapses into particular measurement states. Quantum computers are not a replacement for classical ones, they complement. It's very important. They complement the traditional systems by possibly being able to solve some form of intractable problems that blow up or become extremely large or time consuming during computation. The fundamental steps. So let's start with the loading step. So essentially we need to load the data in the quantum computer in order to perform analysis on it, right? The solution must load its data from a classical computer into a quantum computer in a small number of steps. This results in a superposition which combines the fundamental states described above in a way that reflect the dataset being loaded. While loading data into a computer is often ignored as a triviality in classic compound computing, quantum data loading can be a substantial aspect of solution design. So normally we are very much habituated with just giving random inputs using keyboard, mouse, or any other type of input devices. But in the case of quantum computers, we need to be very careful while in giving data to it, since it can be a substantial aspect of solution design. Next is compute step. This involves the manipulation of the qubits in a manner that changes the fundamental states in a way that reflects the outcome of the desired computation. There is an increasing body of research into quantum algorithms that solve problems that are considered computationally difficult or intractable classically. Quantum computation often compute their results as an approximation to an optimal value within a high dimensional search or space, and often exploit the nature of quantum superpositions to simultaneously consider vast number of possibilities. The computed output superpositions reflects a probabilistic distribution of possible outcomes with preferred outcomes associated with higher probabilities in the distribution. Let's move on to next step, that is measurement step. Wait a second. Measurement step. Yeah. So essentially, measurement step is quantum computers will measure the resources needed for computing it, and if there are resources present, then it will start computing. Now let's move on to have a brief introduction over the financial services, because without that we cannot able to understand the needs of the financial sector. That's what I believe. Financial services are a forward-looking industry that has always been in the lookout to leverage new technologies to increase profits. Broadly, this industry covers three vertical sectors. Banking. Banking products are mainly bank accounts, investments, loans for commercial and retail customers. Their main challenge are to balance cash with interest rates while controlling threats related to liquidity, fraud, money laundering, or non-performing loans. Financial markets focus mainly on future gains and a marketplace to sell and buy assets by dealers, exchanges, brokers, or clearing houses. Their main challenges are to manage geographic time zones, immediacy needs, and counterparty risk. Insurance, health insurance, automobile and property life insurance, and annuity and reinsurance. The main challenge here is to maximize premiums and manage threats related to unplanned risks such as catastrophes or market crashes. Now, at the bottom there is a table which essentially gives a perspective over the legs of these all three bank financial sectors, that is banking, financial markets, and insurance. So let's move on to next slide. So, as you see, transformative technologies in support of digital teams in financial services. If you closely observe the given figure, there is a digital and omnichannel, digitalized process, personalization to data plus AI, open banking ecosystem, self-driven banking. So, financial services are trying to transform themselves in order to be competitive with the growing, with ever fast technology and world, because you know we teenagers are very tech savvy and we need everything tech savvy. So the problem areas, so what essentially is our problems for financial services. Now till now we had a brief introduction over financial services. Next we'll understand the problems it faces. Three areas of financial services where problem challenging for classical computers arise today: asset management, investment banking, retail and corporate banking. So financial services mainly have problems over these three subsectors, that is asset management, investment banking, retail and corporate banking. The adoption of algorithmic trading that changed the stock with high-frequency trading for investment banking, and the increased use of mobile devices for payments impacting financial transactions in retail banking. The adoption of new technologies and evolutions of financial services can be traced in ways leading to a digital future. So how this problem arises is, as goes on, people started using digital processes and digital services to perform asset management, investment banking, and all this stuff. Now, as these need high computational powers to take the orders and execute them. Classical computers are unable to do uh, analysis as well as the taking in orders and executing them. They are not fast enough and they are not capable enough. For that very reason, we need much powerful computational devices like quantum computers to analyze these uh, vast amounts of data that is being generated for every second and give a live analysis of all this data. Okay, so how and why that this occurred? See, the first wave focused on, so it essentially explaining the technology, um, influence of technology over financial services. The first wave of technology focused on mobile adoption to engage customers. This was followed by exploration of new business models to leverage new data sources and a threat from technology providers. The third current wave is driven by a combination of challenging, including cost pressure, technology disruptions, and regulatory changes. So, what are the applications for this? First is simulation. So, we can use quantum computers to perform simulations. How is that possible? Well, there are simulation problems at each stage of the customer life cycle. Here, we need to understand financial services are customer-based services. So, we have, if we are able to solve, if we are going to solve any sort of problem, we need to focus primarily on the customer life cycle. If not, then what is the use of solving the problem? That's why we are solving the problems in the context of a customer life cycle. The simulation focus on creating scenarios of potential outcomes such as impact of volatility, um, on risk, evaluation asset values for pricing or monitoring ecosystem impacts in the market. So customer life cycle is given below. You can check it. Customer identification, the first step of the customer life cycle. Obtain new revenue sources for new value add services such as derivating and blah blah blah. Next is financial products. After that, we have monitor transactions. Allow for a more precise approach into incorporating market volatility into an institution's Tier 1 reporting, optimizing risk-weighted assets results to a much more accurate, precise calculation process. Customer retention, improve risk analysis for the new stable funding ratio timeframes requirements that will impact the cost of doing business for prime brokers and hedge funds. Hedge funds are essentially scam funds. Be aware of them. Stable funding of for securities lending transactions shifts from 0% to 10% for level 1 collateral and to 15% for their collateral. One key task in the finance industry where simulation is crucial is the pricing of financial instruments and estimating their risk. For example, the buyers and sellers of complex financial instruments gain a competitive advantage when they can price such instruments with a better accuracy than their competition. Regulations such as Basel III require banks to perform stress tests and to hold an amount of capital that depends on their risk-weighted assets. However, pricing and estimating the risk of many financial instruments is computationally intensive. Analytical models are often too simplistic to capture the complex dependencies between financial instruments or cannot take account some of their features such as path dependency. Monte Carlo simulations are therefore used to estimate risk metrics, to price financial instruments, and to perform scenario analysis that can be used in stress tests. So we also have option pricing. Now, options are financial derivative contracts that give the buyer the right but not the obligation to buy. Okay, now options provide investors with a vehicle to profit by taking a view on the market or exploit arbitrage opportunities and or go to various hedging strategies. As such, understanding their properties is a fundamental object of financial engineering. Due to stochastic nature of the parameter options are defined on, calculating the fair value can be an arduous task, and that's where quantum computing comes in. Next is risk management. As I said, plays a central role in the financial system. It allows companies, institutions, and individuals to avoid monetary losses and grow their business. Financial risk, which comes in many forms such as credit risk, liquidity, etc., is often estimated using models and simulation. The accuracy of these models has a direct impact on the operations of the entire entity using them. Next application is optimization. Till now, we have studied the applications of quantum computing over simulations, but now it's time for optimization. Customer identification, again, because we are solving the problems in the context of the customer life cycle, so we use the customer life cycle in order to gain insights. Improve financial supply chain efficiency in procurement and payment, focusing on customers and suppliers to increase to reduce working capital levels, enhance liquidity, and so on. So, social products will increase monitor transactions, keep investment portfolios relevant by rebalancing aligned to market changes while handling all associated fees. This can reduce transaction cost by 50% and lead to 600,000 savings in trading costs. For an example of 4 assets, 1 billion portfolio. Customer retention. Improve the process of matching companies to potential buyers to avoid current customers churn towards automated investment banking. This can reduce current work losses. Customer retention can also be done through optimization. Many financial services firms may want to take action that result in the best possible outcome for a given role. In the language of mathematical optimization, finding the best decision or action with respect to maximizing or minimizing given goals or objective, it casts as maximizing or minimizing an objective function in a decision variable subject to constraints often given again by functions if it on a decision variable. Next application would be machine learning. Machine learning focuses on finding relations in data and building assumptions around them for predictions by anticipating future events from historic data, or to classify data by dividing an end result into different categories, or to finding patterns. For example, the investment management strategies and the optimizations and to make use of the estimations of future risk and asset prices that can be obtained from the output of machine learning algorithms. Banks can estimate the risk level of their customer loans by credit scoring, which can be formulated as classification and a regression problem based on the rich customers such as age, salary, and etc. So machine learning is quite helpful. Here also we will use machine learning over the customer life cycle and essentially solve these major problems. Overall, artificial intelligence and machine learning are of deep interest for financial institutions, with a current global spending in the banking industry worth $3.3 billion in 2018, with the hopes to build better classification models that will improve customer service in external facing and internal activities. So let's summarize. There are a number of computational challenging problems in financial services that are demanding in terms of required precision or runtime. For these, we have outlined three problem classes. One is optimization, second is machine learning, third is simulation. Quantum computers and the algorithms that leverage them may help to solve hurdles and challenges arising in the financial industry, given increasing demand for more sophisticated risk analysis, dynamic client management, constant updates to market volatility, and faster transaction speeds. With the slide, I want to summarize and end this event slide presentation. Thanks for listening. I hope you have great insights over how quantum computing is going to have a major impact on financial services and the financial sector as a whole. Let's end this video and have a good day.